Today we want to look at another example of a fundamental theorem of calculus in Green's theorem. Green's theorem is kind of our fundamental theorem of calculus for double integrals. Weird that now it shows up when we've been talking about line integrals for so long, but we kind of need line integrals to talk about Green's theorem. But our structure of a fundamental theorem of calculus is that we can integrate the derivative of a function over a set, and that will be equal to the change in the function over the boundary of the set. Integrate the derivative over a set by evaluating the function at the boundary of the set. So when we integrate our regular fundamental theorem of calculus, our OG fundamental theorem of calculus, we have the integral from a to b of f prime of x to x is f at x evaluated from a to b. Evaluate the function at the endpoints. Specifically, we want to call out the change in the function over the interval. But to pair it up with our structure up here, the derivative of the function is f prime and the function is f. Then the other two players are the set. That would be the over which we're integrating. The set is the interval from a to b, and the boundary of the set is the endpoints x equals a and x equals b. So we see the same four parts in other things that we're going to call the fundamental theorem of calculus. So when we have the fundamental theorem of calculus for line integrals, we integrate over some curve C of vector field dot dr. Oops. I'm so used to just writing the generic line integral. I forgot I wanted to write a fundamental theorem of calculus for line integrals. So we integrate over some curve the gradient of a function. Now remember, the gradient of a function will be a vector field, but the function itself, in this case f, the potential function, is just a scalar function. So since this is a vector field, gradient of f, we find the dot product with dr, and this will be just the potential function evaluated at the endpoints. In this case, we still have the same four players. Our set is any path from P to Q. It can be any path from P to Q because we found gradient fields are conservative. That is path independent. The boundary of the set is the endpoints P and Q. The derivative of the function is the gradient. So the gradient is standing in for the derivative of the function. So I'm going to put it in quotes in case anybody thinks I'm being fishy. So we still see the same four parts. The integral of the derivative of a function over a set is equal to the change in function over the boundary of the set. Really, our fundamental theorem of calculus for line integrals is just our fundamental theorem of calculus along a curve. So we've got a point P and a point Q. The fundamental theorem of calculus for line integrals just says, well, we're integrating a gradient field, then it doesn't matter what path we take. This is just a curvy version of our original fundamental theorem of calculus. Our original fundamental theorem of calculus started at A and ended at B, and because we only had one variable, we really couldn't do anything other than make an interval. There's only one way to get from A to B. But in a plane, there are uncountable infinity of ways to get from point P to point Q. And in a gradient field, it doesn't matter which one we take. So the line integral version of the fundamental theorem of calculus is the same fundamental theorem of calculus, just curvy. Fundamental theorem of calculus for line integrals is the bendy version of the fundamental theorem of calculus. Yeah, so we have two different with a gradient field. With a gradient field is path independent. So it doesn't matter which path we take from P to Q. If our vector field that we're integrating in our line integral is a gradient field, then any path will give us the same result. So here, P and Q are points in the plane. P and Q are points in the plane, and C1 and C2 are any path from point P to point Q. So this is like the problem that we did in week 12, on Thursday and Friday. Problems 124 and 125. We had a gradient field in both of those line integrals, and we had two different paths, or three different, I don't remember how many, 2 or 3 different paths from one point to another, and we were getting the same result. That's because in those problems we had a gradient field. We're not really integrating under the curve because we're not calculating an area. So we're thinking about the multiplication. When we think about area under the curve, we're using just regular old multiplication as our multiplication. Integration is multiplication, but one of the factors is continuously variable. So the model that we use in our regular fundamental theorem of calculus is area under the curve, because that's length times width. That's our multiplication. But in the fundamental theorem of calculus for line integrals, our regular multiplication is not length times width. It's not representative of an area. It's a dot product. We're calculating a dot product. So we're doing a multiplication, but we're doing multiplication at an angle. And so area under the curve doesn't really apply. We're not really thinking of it in terms of area under the curve. We're looking at what the angle is between the vector field and the path, the direction of the path, tangent to the path. And we're multiplying those two, but since we're multiplying at an angle, we're using a dot product. One thing that we haven't calculated so far is we haven't applied the fundamental theorem of calculus for line integrals in 3-dimensional space. But it will work the same. We can have a potential function, look at the gradient, integrate a gradient field from over any one-dimensional path in 2 or 3-dimensional space, and we can just subtract the endpoints, the potential function at the endpoints. It's easier to draw pictures when we're in R2. So there's our structure of how we think of things that are fundamental theorems of calculus. We integrate a derivative of a function over a set by evaluating the function at the boundary of the set. So I put the gradient here as, in quotes, as the derivative. It's kind of taking the place of the derivative. And we're going to have more derivatives because I keep talking about this fundamental theorem of calculus structure. So we're going to have more things that are fundamental theorems of calculus. But they are going to have this same shape. When something is called a fundamental theorem of calculus, this is the structure that you're going to want to look for. You're going to want to look for a derivative of a function. You're going to want to look for a function. You're going to look for a set, and then the boundary of the set. So let's talk about me being all fishy and calling the gradient the derivative of the function. When we think about derivative in single variable calculus, we think about derivative as how things are changing. What's our rate of change? Derivative is telling us the rate of change. And we could get away with that kind of easy description of derivative because in single variable calculus, there is a single variable. And it's only changing in one direction. It can either increase or decrease, but the decrease is just -1 times an increase. So when we say, how is this changing? How is the function changing? When x increases. Specifically, when we're looking at the slope, when x increases by 1. So at that moment, what is the instantaneous rate of change of the function? We are talking about how much is the function changing if x increases by 1. Because there's only one direction to go. But when we think about a function of 2 variables, we have 360 and we're looking at a point, we have 360 degrees of direction to go. There's some x direction and there's some y direction. There's some x direction and some y direction. The gradient is telling us which direction gives us the maximum amount of change. Because it's not useful as an answer to say how much are things changing. So, well, it depends on what direction you're going. So the gradient is telling us what direction is the maximum change, and then we dot product to find the change in any direction that we happen to be interested in. So in single variable calculus, derivative is very simple because there's only one direction where the inputs are changing. When there's one direction of inputs is changing, derivative as a rate of change, very simple. How much is the function changing when x increases by 1? But for a function of 2 variables or a function of 3 variables, we have much more direction. So it's useful to think about the gradient, which is what is the direction of maximum increase? And then if we're going in some other direction, we can use the dot product because the dot product is multiplication at an angle. So that's the thinking part of the gradient as the derivative. That's the thinking part of the gradient as the derivative. The kind of functional part of gradient as derivative, if we think about a function, a potential function, We need something that we want to call the derivative, so we're going to have the gradient stand in as the derivative. Now, what we did in the fundamental theorem of calculus for line integrals was we kind of started at this derivative part. We kind of started at this derivative part and looked at a function and asked the question, is this the gradient of some function? So if we imagine ourselves starting with this vector field, and we can ask, and we're asking ourselves, is this the gradient of some potential function? So when we're just looking, when we're starting here with the derivative, we're asking ourselves, is this a gradient field? Is there some potential function for which this is the gradient? Can we integrate this? Is this scalar function f1 the derivative of something with respect to x, and f2 is the derivative of something with respect to y? One way we can determine this, is to just try to integrate and see if there is one. So we want to know, can we go from the gradient up to a potential function? Let me write down this guy. So can we take, say, f1 is our partial with respect to x, and can we use that to find our function f? And if f2 is some partial with respect to y, can we use that to find some function f? I think it's coming up Monday today. I didn't like the way that looked. So if we say f1 is the partial with respect to x, and f2 is the partial with respect to y, can we take these two pieces of information and from them construct one potential function? One way we can find this out is to actually go further in the derivatives, go one level down from the derivatives. And we think to ourselves, well, if fx and fy, if those are the first partials of some potential function, then the mixed second partials should be equal. So our thinking, going one level down, is to say, if f1 and f2 are fx and fy, if these two functions are first partials of some potential function, then the mixed second partials will be equal. This is a function of x and y. I was just abbreviating. So we could think that f is, this is a function of x and y. f1 is a function of x and y. and f2 is a function of x and y. And the same is true with our f1 and f2 up here. I'll just abbreviate it. So now what we're going to think is if f1 and f2 are first partial derivatives, then the mixed second partials should be equal. So when we're asking the question, is this a gradient field? We might think if f1 and f2 are first partials, if f1 and f2 are first partial derivatives of some potential function f, then the mixed second partials should be equal. So if we imagine starting with a vector field f, and we want to know if it's a gradient field, one way to find that out is to look at the mixed partial derivatives of our functions f1 and f2. So what we'll check is that the partial of f1 with respect to y is equal to the partial of f2 with respect to x. In terms of the gradient field, we're asking the question, we're trying to verify if fx, partial of f1 with respect to y would be fx with respect to y. And the partial of f2 with respect to x will be fyx. If these things are equal, then we can conclude that the given vector field, starting from a vector field, not knowing if it's a gradient field, asking the question if a given vector field is the gradient field, by checking to see if the mixed second partial derivatives are equal, then we'll find out if it's a gradient field. So when we are checking if the partial of f1 with respect to y is equal to the partial of f2 with respect to x, we could think of this as, when these two things are equal, we could think of their difference being 0. So that is the same question. And the reason that I want to gather these things up is that the partial of f2 with respect to x minus the partial of f1 with respect to y, this has a name. This is the curl of the vector of the potential function. This is the scalar curl, so it's only going to work on vector fields with two variables. So this expression here is the curl of the vector field. Specifically the scalar curl. The scalar curl is the one that applies to vector fields in R2. There's also a vector curl, which will apply to vector fields in R3. So let's take a look at Green's theorem and see how it fits in the structure of fundamental theorems of calculus. So here are the things that we want. We got a vector field in R2. Green's theorem is going to be a vector field in R2. It's going to apply to vector fields in R2. And we've got some region in R2 with the boundary C, oriented with the region on the left. So C has counterclockwise orientation. It's not exactly round, but so let's put this in quotes. And then let's draw a picture. So we've got some region, and C is the boundary of the region. Not of R, just R. And we have this region R. When we have a parameterized curve in R2 or R3, it has some orientation. We want the orientation to be roughly counterclockwise. We want, as we travel along the curve, the region to be on the left. So this would be the orientation of the region. Green's theorem is going to act as the fundamental theorem of calculus for double integrals. That's the way we're going to think about Green's theorem. So Green's theorem says that the integral around C of this vector field dot dr. If we look at the integral, the line integral around the boundary, this is equal to the double integral over the region of the curl of f. This is sloppy of me to write it this way because I'm writing the curl of the vector field, but it's specifically the scalar curl of the vector field. So to write this in a better way, well, I've implied it's a scalar curl because I said the curl of f just times dA, not dot dA. But to avoid that, we just write the curl of f with his definition. In the structure of a fundamental theorem of calculus, the scalar curl is acting as the derivative. And I'll put that in quotes because that is very fishy for me to phrase it this way. So that curl, the scalar curl, is acting as the derivative of our function, which is the vector field. Our function is the vector field. The fundamental theorem of calculus, a fundamental theorem of calculus will say integrate the derivative over some set. So R, the region R, is the set. And the boundary of that set is the curve C. Specifically for this to work, we have a closed curve. So Green's theorem we want to think of as our fundamental theorem of calculus for double integrals. Pause for copying. Oh, I'm not supposed to read that part on the telephone. Let's think about this in the context of our fundamental theorem of calculus for line integrals, because this theorem, Green's theorem, does in fact involve a line integral. The double integral over the region of the curl of the function, the scalar curl of the vector field, will be equal to the line integral of the vector field around the boundary of the region. So there is a line integral in here. Let's think about what happens if we have a gradient field, and then the fundamental theorem of calculus for line integrals applies. So notice that the curve C, since it's the boundary of some region R, a closed curve means that the starting point and the ending point are the same. Starts and ends at the same point. So the closed business means starting and ending at the same place. So if we start here at P, we also end here at Q. The starting and ending points will be the same. That's the closed part of the closed curve C. If F is a gradient field, then if F is the gradient field, if F is a gradient field, that it is a gradient field for the gradient field of some potential function F, then when we integrate over the curve a gradient field, we'll just have F at Q minus F at Q because the starting point and ending points are the same. Or F at P minus F at P, since the starting and ending points are the same. And in both cases, we'll end up with 0. Remember, we're starting and ending at the same point. On the other side, if F is a gradient field for some potential function F, then the scalar curl will be equal to 0. So over on the other side, we'll be doing a double integral of 0. If we're looking at a gradient field, that means there's a potential function. That means the mixed second partials will be equal. And so the scalar curl will be equal to 0. That is a way of finding out if we have a gradient field. And so our double integral over the region will be of 0 dA, and that'll be 0. We haven't done any calculations with Green's theorem. We want to describe Green's theorem as a fundamental theorem of calculus. Think of it as the fundamental theorem of calculus for double integrals. Remember your structure for a fundamental theorem of calculus. Imagine integrating over a set, and then imagine the boundary of the set. expand what we think of as derivatives. We think of the gradient as the derivative of some potential function. We can think of the scalar curl as the derivative of a vector field in R2. All right, so we'll look at more examples of Green's theorem tomorrow. That's going to do it for today. I'll see you all on tomorrow. But have a good day, and thanks for playing.